Okay, so today in Math 175, we're going to be dealing with 4.1 and 4.2, and they kind of both focus on graphs of polynomials. So we're going to go ahead and we're going to start. The first thing we're going to talk about is we're going to talk about the degree of a polynomial. Now, the degree of a polynomial is the highest exponent, right? So we're dealing with the highest exponent. Now, what this really means is the degree kind of dictates the shape and a lot of other things about the graph. So for instance, we're going to start with very basic and kind of work our way up of what you're going to see in this section. We're going to start off kind of basic, and we're just going to deal with f of x equals 3. Now, f of x equals 3, that could be rewritten as 3x to the 0. So we would say that the degree of this polynomial is 0. That means that this particular polynomial is a constant polynomial. Now, the graph of a constant polynomial, if you remember, is just a horizontal line. Okay. So now we're going to work our way up. So the next graph we're going to look at is f of x equals 2/3 x plus 5. Now 2/3 x plus 5 has a degree of 1. The highest exponent above the x is a 1. So the degree is 1. Now this is what algebra 1 is all based off of. These type of functions are linear functions. The graph of a linear function is a line that looks like this. Now, I'm not necessarily graphing these functions. These are just examples of it, okay? Next, we have f of x equals 4x squared minus x plus 3. The highest exponent is 2, so we have a degree of 2. Now, a degree of 2 leads us to a quadratic polynomial. The graph of a quadratic polynomial, we know, is a parabola. Okay. Next, we have the graph, or the function, x to the third plus 2x squared plus x minus 5. The highest degree is 3. So we have a degree of 3. And this is referred to as a cubic polynomial or a cubic function. A cubic function could look something like this. Okay. And we'll talk more about all of these. Last is we have negative x to the fourth minus 1.1 x to the third plus 0.3x squared minus 2.8x minus 1.7. Now the degree of this, we have a degree of 4. And this is referred to as a quartic function. Now a quartic function, these kind of look like a W. All right, well, this one's going to look like an M. You might have something that looks like that. Now, what I want to point out is I want to point out that the degree means something about this graph, okay? The degree is how many times it's going to cross the x-axis, the most amount of times it could cross the x-axis. So a constant function isn't crossing the x-axis at all. A linear can cross the x-axis a maximum of 1 time. A quadratic can cross it a maximum of 2 times. A cubic, a maximum of 3 times. And a quartic, a maximum of 4 times. Okay? Notice I'm saying a maximum of that because they don't have to cross it that many times. We've done some work with quadratics before. You know that it can have 1 x-intercept or none, but it can have a maximum of 2. Now, a cubic isn't necessarily going to cross the x-axis 3 times. It's just going to cross it a maximum of 3 times. Same thing with a quartic, a maximum of 4 times. Okay, now we're going to talk about a little bit about the graphs of a polynomial. Okay, so here I have on the left, I have some graphs of polynomials, similar to the ones that you just saw. Then I drew some graphs of non-polynomials, and we're going to kind of look at the difference here. What I want you to notice is that polynomials are all smooth curves. We don't have any points, we don't have any ridges. They're all smooth to draw, unlike this absolute value function that has a point. This other function that I don't even know what it is, but it has points in it, right? It looks like they're all rough. Here, polynomials are all smooth curves. Also, what you'll notice about a polynomial is, well, let me write that down first. They all have smooth curves, or as smooth as they can get, right? Another thing I want you to realize is that there's no breaks in these lines. There's no jumps like this over here. It's just one continuous line. So polynomials are what we call continuous. There's no gaps, breaks. They're all just one solid line. Another thing we want you to look at is that the domain of this, there's no restrictions on the domain. So your domain is going to be all real numbers, or what we call from negative infinity to positive infinity. And so we don't have any breaks in the line over here, and here we don't have it terminating and not continuing, and there not being values of x that don't have an output, right? So that would be a limitation on the domain. Polynomials all go from negative infinity to positive infinity. There's always going to be an output for any value of x. Okay, the next thing we're going to talk about is we're going to talk about the leading term test. The leading term test, it determines the ending behavior of the graph. We're going to talk more about what that means as we go through some examples. But it determines the ending behavior of the graph. I guess I'll explain it now. A polynomial's end behavior is what happens at the very end of the graph, where those arrows are pointing. So we would say this graph rises to the right, where the right side rises. That means that this arrow is pointing up. As you continue right, that graph's going to continue to go up and up and up. We would say that this particular graph, that it falls to the left. So the left side of it is going to fall. Now, just by looking at the equation of the graph, or the equation of the function, you can determine whether or not what these ending behaviors are, what it does to the right, what it does to the left. The first thing we're going to talk about is we're going to talk about the right side, how to determine the right side. Now, you have to determine what the right side does first before you determine what the left side does, because the left side is dependent on what the right side does. So the right side controls it. So the right side, if the leading coefficient is positive. Now, the leading coefficient, that is the coefficient on that highest degree term. When it's in standard form, so descending order of exponent, that leading coefficient is the number in front of that highest degree variable. All right, so if the leading coefficient is positive, the right side rises. So now, if the leading coefficient is negative, it does the opposite of that, right? So if the leading coefficient is negative, the right side falls. Okay, so here the right side rises, so the equation would be, would have a positive leading coefficient. Now we are going to be looking at examples of this, okay? So now the next thing, once we determine what the right side does, we have to then determine what the left side does. Now the left side is all dependent on the degree. So the right side is dependent on the leading coefficient. The left side is dependent on the degree of the polynomial. That's that highest exponent. So here's the rules. If the degree is even, the left side does the same as the right. So if the left side is even, it does the same. Okay. So if your right side rises and your left side, and your degree is even, your left is going to also rise. Now, reverse of that, or opposite of that, if the degree is odd. So if it's an odd number, like 1, 3, 5, 7, okay, you're not going to see anything above 5, maybe. So the left side does the opposite of the right. Okay. So if your degree is odd, the left goes the opposite way. So let's say our right side fell and our degree was odd. So if the right side fell, the left side would rise. It does the opposite of that. That's why you have to determine what the right side does first before you go and determine what the left side does. Now I'm going to make a little chart for you. We are going to be talking about the leading coefficient being positive and the leading coefficient being negative. Then our degree is going to be even, and our degree is going to be odd. Just making a little chart to make it a little easier for you to see. Maybe something to look at, those visual people out there. So we have 4 different scenarios here. If our leading coefficient is positive, your right side is going to rise. If the degree is even, your left side will also rise. That's your parabolas. That's your going up. The right side and the left side both rise. Okay? If your leading coefficient is negative, your right side is going to fall, and your degree is even, your left side is going to do the same thing, so it is also going to fall. So that is your downward facing parabola. So the right side fell and the left side fell. Now this box has a positive leading coefficient and a degree that is odd. So a positive leading coefficient means the right side is going to rise. A degree that's odd means that the left side is going to do the opposite of the right side. So if the right side rises, the left side is going to fall. So our right side is going to go up, our left side is going to go down. That is very, very common of a cubic, a degree of 3. Because we have a right side rising, left side falling. Now, our last scenario is a leading coefficient that is negative and a degree that is odd. So if your leading coefficient is negative, your right side is going to fall. If we have a degree that is odd, our left side is going to do the opposite of our right side, and it's going to rise. So our right side fell, our left side is going to rise. So we have that other cubic here. So our right side fell, our left side rose. Now we're going to go through some examples of this. Okay, so the first polynomial we're going to look at to determine the ending behavior of it and do the leading term test to it would be 3x to the fourth minus 2x to the third plus 3. All right, so we are going to identify first that leading coefficient. Now, leading coefficient is a pretty long word to write. I hate writing it all the time, so I abbreviate it as LC. So when you see me writing LC, I mean leading coefficient. So our leading coefficient, that is our first number, the number that's in front of our highest degree term. So that in this case would be 3. Now the only thing that matters about that 3 is positive. So what does that mean? That means that the right side is going to rise. Okay, now we look at the degree of a polynomial. So the degree of this polynomial is 4. That's that highest exponent. So we have a degree of 4. Now the only thing that matters about that 4 when you have a leading term test is that it is even. So we have a positive leading coefficient, so the right side rises, and we have an even degree, so the left side is going to do the same thing as the right, so they're both going to rise. Now, an example of what this graph is going to look like is this will be a quartic, right? They're going to both rise. So it could look something like that. Now, I don't know what really happens in here. The only thing I'm concerned about right now is that they are both going to go up. We are going to talk more about how to find the x-intercepts and the y-intercepts to sketch a more accurate graph. Right now, I just drew a possible quartic with both of our ending behaviors rising. Next, we have the function f of x equals negative 5x to the third minus x squared plus 4x plus 2. All right, first thing we got to look at is that leading coefficient. What is that number, the first number that you see in front of that first variable? That would be negative 5. The only thing that matters there is that that is a negative number. Now, what does a negative leading coefficient mean? It means that the right side is going to fall. Now we take a look at the degree. The degree is 3. So if the degree is 3, the only thing we worry about there, 3 is an odd number. So what does that mean? That means that the left side is going to do the opposite of the right side. So the right side falls, right? So the left side is going to rise. So our right side is going to fall, our left side is going to rise. Now what happens in here? I don't know, but I'm going to take a good guess, and I'm going to draw some kind of cubic. So our right side fell, our right side rises. Next is we are going to look at x to the fifth plus 1/4 x plus 1. Our leading coefficient here, there's nothing in front of here, so there's really a 1. So our leading coefficient is 1. So that is a positive number. So our right side is going to rise. Our degree, our highest exponent is 5. And that is an odd number. So our left side is going to do the opposite of our right side. So our right side rises, our left side will do the opposite of that, and it's going to fall. So our right side rises, our left side falls. This is a 5th degree. There could be a lot of things that happen in here, all right? Just completely guessing in there, whatever happens in here. All that I'm worried about right now is that the right side goes up and the left side goes down based on our ending behavior. The last leading term test, the example that we're going to look at is negative x to the 6th plus x to the 5th minus 4x to the 3rd. Now our leading coefficient is really -1. There's really a 1 there in front of that negative or next to that negative. So that is a negative number. So that means that our right side falls. Okay. And then the degree of this polynomial is 6, and 6 is an even number. So that means that the left side is going to do the same thing as the right side. So the left side is going to fall, okay? A common mistake that I see all the time is people feel that if the degree is even, the left side always rises. If the degree is odd, the left side always falls. That is not the case, right? The degree tells whether or not it does the same or different or opposite than the right side. So here we had a degree that was odd. The left side did the opposite of that. Here we had a degree that was even, so our left side did the same thing as the right side. So here they both fall, so we know our left and our right side are both going to go down. I don't really know what happens in here. There could be a bunch of squiggles, but all I know is that the ending behavior both falls. Okay, this is a pretty complicated looking polynomial. We're not going to be drawing anything that looks that crazy. All right, the next thing we're going to look at is we're going to look at how to find the zeros of a polynomial and what that means. Okay, zeros, solutions, roots, and x-intercepts. These are words that you may hear quite often in courses, this course and other courses higher up than this. Zeros, solutions, roots, x-intercepts. These all mean the same thing, just in different circumstances. A zero, a solution, a root, and an x-intercepts are all found the exact same way. What they are is they come from values of x that output to 0. There's values of x that make the y 0. Same definitions we have for x-intercepts. Same thing we practiced when we were solving polynomials. We were solving quadratics, when we were factoring and applying the zero product property. We were all finding them the same exact way. Okay, so if we are given the polynomial p of x equals x to the 3rd plus x squared minus 17x plus 15, right? We are asked to determine if 2 and -5 are zeros of p of x. So are 2 and -5 zeros of this? What does that mean? That means that if they get plugged in for all of the x's, will they output to 0? So let's figure that out. If I take 2, p of 2, and I plug it in, I have 2 cubed plus 2 squared minus 17 times 2 plus 15. And I evaluate this. 2 cubed is 8 plus 2 squared, which is 4, minus 17 times 2, which is 34, plus 15. I know I'm kind of going out of order of operations a little bit, but it doesn't matter in this case. So 8 plus 4 is 12. 12 minus 34 plus 15. 12 minus 34 is negative 22 plus 15. Negative 22 plus 15 is negative 7. So is 2 a 0 of this polynomial? No. It outputs to negative 7. So we're looking at 2, negative 7, and that's not an x-intercept. That is a point on the line, but that's not an x-intercept of that. Next thing is we have to determine if negative 5 is a 0. So we have negative 5 cubed plus negative 5 squared minus 17 times negative 5 plus 15. So negative 5 cubed is negative 125. Negative 5 squared is positive 25. All right, remember that a negative to an odd power is negative, but a negative to an even power is positive. All right. Then I have a negative 17 times negative 5 would be positive 85 plus 15. Negative 125 plus 25 is negative 100 plus 85 plus 15. Negative 100 plus 85 is negative 15. Negative 15 plus 15 is 0. Okay, so we're looking at the point negative 5, 0. Does negative 5 output to 0? Yes. Negative 5 is a 0 of our polynomial x to the third plus x squared minus 17x plus 15. All right. What we're going to do now is we're going to go over again how to find zeros of polynomials and the certain situations and how they connect to sketching our graph. Okay, so how do you find zeros? We've done it in the past. You just didn't know what you were doing, right? You just knew that you were solving a polynomial or solving a quadratic. We're going to apply the zero product property. So for instance, our first example is we're doing f of x equals x times x plus 3 times x minus 4. We have to find all the values of x that make this equal to 0. So we have 0 equals x times x plus 3 times x minus 4. So is there a value of x that makes x 0? Yes, 0. Is there a value of x that makes x plus 3 equal to 0? Negative 3. So by subtracting, we set x plus 3 equal to 0, and we subtract 3 to get the negative 3. Is there a value of x that makes x minus 4 equal to 0? Yes, x would equal 4. So we have zeros of 0, negative 3, and 4. Okay, so what this means is that our graph, our polynomial, is going to cross at negative 3, 0, and 4. Now, this is a cubic, so we are going to have a degree of 3. So our ending behaviors are going to be opposite, and it's going to have a positive leading coefficient, so it goes up. Don't worry about that right now. All right. What I want you to concentrate on is that this polynomial is going to cross the x-axis 1, 2, 3 in each of these places. So we're crossing, we're curving back around, we're crossing again, and curving back around, and then crossing again. So we have to cross in those 3 spots based on that. So moving on to number 2. Number 2, we have a polynomial of negative 3 times x plus 2 squared times x minus 1. So we have a binomial here that's squared. What does that mean? We know what that means. that means that I have to write it twice. Okay. Now, don't worry, I'm not going to multiply it together to determine what the polynomial is. I'm just going to write it twice and apply the zero product property to it twice. Now, we have a constant out front, that -3. Do we have to worry about that when we're doing zero product property? No, because it doesn't have an x there. So there's no way to get that -3 equaling 0. That's kind of just along for the ride. So what makes x plus 2 0? -2. Now, -2 also makes that a second x plus 2 0. We're going to talk about what it means when we get two of the same zeros. And don't forget, we still have that x minus 1 equaling 0. So we have 1. So our zeros here, right? So we have zeros of -2 and 1. But this -2 appears twice. We refer to that as a multiplicity. A multiplicity. And because it happens twice, we say that -2 has a multiplicity of 2. Because it happens twice. Now, 1 just happens once. So we could write that it has a multiplicity of 1, but that's just common. So we really don't write that it has a multiplicity of 1. But because the -2 happens twice, we say that it has a multiplicity of 2. So what does that mean? What does it mean when you have a multiplicity of 2? Does it react differently? Yes, it does. So we have zeros of -2 and 1. So what this means, a multiplicity of 2, means that we are going to bounce off the x-axis. We are not going to cross it like we do with multiplicities of 1. We're going to bounce off of it. So it happens twice. So you touch it, and then you go back where you came from. Now, 1 just had a multiplicity of 1, so we're going to cross through it. So -2 has a multiplicity of 2, so we bounce off of it. Or the book will tell you that that's where a tangent line is, but I think it kind of hits home, kind of makes a little more sense that it bounces off the x-axis when we have a multiplicity of 2. And then when we have a multiplicity of 1, it goes through it. Let's look at another example. Example number 3. We have f of x equaling negative x minus 1 squared times x plus 2 squared. So what does this really mean? Well, we can write it as -1 times x minus 1 times x minus 1 times x plus 2 times x plus 2. So we would have zeros, right? What makes x minus 1 0? 1. What makes x minus 1 0? 1. What makes x plus 2 0? -2. What makes x plus 2 0? -2. So what are our zeros here? We have zeros of 1, and 1 has a multiplicity of 2, and -2 also has a multiplicity of 2. So they are both going to bounce off the graph. So we have -2 and 1. Just going to put somewhere on an x-axis, and we're looking at the graph bouncing off -2, turning around, going towards 1 again, and bouncing off 1. So it's going to bounce off -2, bounce off 1. Right? We have an even degree. If you multiply this all together, you would have an x to the 4th, and then that leading coefficient would be negative. That's why they're both falling. One more example I wanted to show you. Let me move my graph up a little bit, or my page up a little bit so you can see it. Hopefully I don't squish it in here too much. Is we have f of x equaling x to the fourth times x plus 4 to the third. Okay, so if we have x to the fourth times x plus 4 to the third, we're really looking at x times x times x times x times x plus 4 times x plus 4 times x plus 4. So we would have 1, 2, 3, 4s, 1, 2, 3, 4 zeros that are 0. So I know it's kind of doesn't make sense, right? So our zeros would be 0. 0 would have a multiplicity of 4 because it happens 1, 2, 3, 4 times. Now, x plus 4 happens 3 times. What is the 0 of x plus 4? What makes x plus 4 0? Negative 4. Now, negative 4 has a multiplicity of 3. Now, here's some new multiplicities. We have a multiplicity of 4 and a multiplicity of 3. Let's see what happens here. So we have something happening at negative 4 and something happening at 0. Now, a multiplicity of 4 is the same thing and acts the same way as a multiplicity of 2. So even multiplicities, and I'll give you this on the next page, right? Even multiplicities bounce off, while odd multiplicities go through. So this particular graph, that negative 4 has an odd multiplicity, so the graph would go through it. Sometimes it does some funky thing, like it flattens out. If you look at graphs, you might see some weird movement happening through here on different multiplicities, but it goes through it. And then because 0 is a multiplicity of 4, it's going to bounce off of it, okay? So because negative 4 had a multiplicity of 3, and it was an odd multiplicity, it went through it, and an even multiplicity bounced off of it. Okay, so here's the rule I was just talking about. Even multiplicities bounce off the x-axis, and odd multiplicities cross the x-axis. That's in my own words. If you read it in a book or watch another video, they're going to say different things about, instead of bouncing off, they're going to say that it is tangent to the x-axis, which means it hits just in one spot, and odd multiplicities crossover. I don't know exactly how they're going to explain it, but that's how I explain it. Okay, so let's take a look at another example. Well, I guess we'll call this example number 5. Example number 5, I'm just going to tell you that the zeros that we have zeros of negative 5, and negative 5 has a multiplicity of 2. It has a 0 of 2, but 2 has a multiplicity of 3, and 4, I don't know why I'm writing this, but it has a multiplicity of 1. If it has a multiplicity of 1, you don't have to write that it has a multiplicity of 1. So what is this going to look like? Let's just follow those rules again. We have something going on at negative 5, something going on at 2, and something going on at 4. So negative 5 has a multiplicity of 2. That is an even multiplicity. Right? 2 is an even number. 3 is an odd number. And 1 is an odd number. Even multiplicities bounce off the x-axis. So at negative 5, we are going to bounce. Okay? 2 has a multiplicity of 3. So that means that it's going to cross through. And then 4 has a multiplicity of 1. It's an odd multiplicity. So it is also going to cross through. So we have a multiplicity of 2 here that bounces, a multiplicity of 3 here that crosses, and a multiplicity of 1 here that crosses. Right? Because we are even, odd, and odd. So bounce, cross, cross. All right, one more example of this. Now, all of the examples that I've given to you, the polynomial has already been factored for you. Let's do a couple that aren't factored, at least one that's not factored. So number 6, if I gave you the polynomial f of x equals x to the third minus 2x squared minus 9x plus 18. And I asked you to find the zeros of this polynomial. Well, you would set it equal to 0 first, and then you would look at how to factor this. Now, this is a 4-term polynomial. If we look across all of this, we don't have a greatest common factor of all 4 of them. So a 4-term polynomial, you then have to factor by grouping. This was in an earlier section that we did, factoring by grouping. I believe it was section 3.2 if you want to go back and look. So our greatest common factor of the first 2 terms is x squared. If we remove an x squared from each, we're left with x minus 2. Now, what can I take out of the second 2 that would leave me with x minus 2? That would be negative 9. So the greatest common factor of the first 2 terms was x squared, leaving us with x minus 2. The greatest common factor of the second 2 terms was negative 9, leaving us with x minus 2. Now, these are both x minus 2, so we pull those out. And we are left with x squared minus 9. Now, that is factored by grouping, but it is not factored completely. X minus 2 is. That's factored completely. But x squared minus 9 is a difference of 2 perfect squares. So this is x squared minus 9 would become x plus 3 times x minus 3. Okay, so now I have to apply the zero product property to this. What makes x minus 2 0? What makes x plus 3 0? And what makes x minus 3 0? That would be 2, negative 3, and 3. So what are our zeros? Well, exactly that. 2, negative 3, and 3. They all have multiplicities of 1. So if we went to go graph this, do a quick little sketch, we have something going on at negative 3, something going on at 2, and something going on at 3. So they are all going to cross. Multiplicity of 1 crosses, multiplicity of 1 crosses, multiplicity of 1 crosses. We have something going on. Now, I don't know how high or low these go. I'm not concerned about that. All I'm concerned about is what happens here, here, and here. What we're going to get into next, and this is more 4.2 than 4.1. All of this stuff was 4.1. Now 4.2 brings it all together. Actually, I'm just going to tell you one quick little fact, right? The next thing we're going to talk about is we're going to talk about how to find y-intercepts. Okay. Now, y-intercepts are found, you could find them 2 ways. You can plug in 0 for x and then get the output, and that would be the y-intercept. Or another way you could find a y-intercept in a polynomial is you can just look at the constant term. So it equals the constant term. So for instance, I'll just go with this example we have here. x to the third minus 2x squared minus 9x plus 18. The constant term is the term without the variable. So this has a constant term of 18. So our y-intercept, where it crosses the y-axis, is going to be the point 0, 18. If you think about it, if you plugged in 0 to this polynomial, this would become 0, that would become 0, and that would become 0. So you'd have 0 plus 0 plus 0 plus 18. It's the same thing as plugging in 0 for x, looking at that constant term. All right, now we know how to find ending behavior, we know how to find x-intercepts, and we know how to find the y-intercept. Let's wrap that all together and really work on creating not very detailed sketches of polynomials, but just kind of bringing it all together and creating kind of accurate sketches. There's still some things that we're not going to know. Okay, so sketching graphs of a polynomial, of polynomials. This is really 4.2. Now, one thing I want to talk about in section 4.2 is if you look through the section, they're going to be referring to steps. I follow pretty much the same steps, except I take out a couple steps. I do not talk about the graph being above or below the x-axis. To me, that kind of makes sense with the crossing and bouncing off. I also do not find extra points. So when you're going through the 4.2 homework and they say refer to the steps on a certain page, you can go through those steps. And I'm following the same order. I'm just skipping, I believe, step 3 and the last step of finding extra points, but I still go through and I find the leading term. Then I find the zeros or the x-intercepts. Then I find the y-intercept. Then I wrap it all together. So my steps that I follow is I find the ending behavior. Okay. That's the leading term test. Then what I do next is I find the zeros. That's what we just went over, finding the x-intercepts. And then I go ahead and I find the y-intercept. Okay, so just the steps here that I'm going to follow is I'm going to find the ending behavior with the leading term test, right? Leading term test, LTT, the zeros, and then the y-intercept. So here, if we look at a leading term test, we have h of x equals negative 2x to the fourth plus 3x to the third. All right, the first thing I'm going to find the ending behavior of this. So the first thing I have to do is I have to look at the leading coefficient. Now our leading coefficient is negative 2. That leading coefficient is negative. So that means that our right side is going to fall. Then I take a look at the highest degree. Our highest degree is 4. Now, what matters about the degree is that it is even. What that means that our left side is going to do the same thing as our right side. So if our left side falls, if our right side falls, our left side is also going to fall. So that's important information right there. Our ending behaviors, that our right side falls and our left side falls. Then step 2, finding the zeros. So I'm going to take that polynomial and I'm going to set it equal to 0. Then I have to factor this. Very first step of every factoring problem is to factor out a leading coefficient. So we're looking at factoring out our greatest common factor, but we have to look at our leading coefficient. Our leading coefficient is negative. So we have to at least factor out a negative 1. And then we have an x to the fourth and an x to the third. So I can factor out an x to the third from each of them. So when I do that, I am left with positive 2x minus 3. So negative 1x to the third, what would make negative 1x to the third 0? Well, that would be 0. Now, how many zeros does that break into, right? 0 is going to have a multiplicity of 3. Okay, that counts for 3 of the zeros because x to the third is really x times x times x. I could have broken it down and wrote it as x times x times x, but 0 has a multiplicity of 3. That is one of our zeros. And 2x minus 3, if I set that equal to 0, x would equal 3 halves. Now that just has a multiplicity. Spelling multiplicity is always tricky sometimes. Multiplicity of 1. So we know that we are going to be crossing at 3 halves and also crossing at 0 because they're both odd multiplicities. So we're going to be crossing at each. Okay, so that's kind of our second thing. Could have wrote that a little neater. Step 3, our y-intercept, is we have to take a look at our, I'm just going to write this here again, h of x equals negative 2x to the fourth plus 3x to the third. Now, is there a constant term here? There is not one shown. What we could do is we could add 0 onto the end of it. So our constant term is 0. So our y-intercept is the point 0, 0. All right. So we know we have the ending behavior of both falling. We're crossing at 0 and we're crossing at 3 halves or 1.5. And we're also crossing at 0, 0, which we already knew. So let's go through and let's sketch this graph. So we know we have something happening at 0, 0, and we know we have something happening at positive 3 halves. Right? So at 0 and at 3 halves, which is really 1.5. So we know we also have our ending behaviors of going down and going down. So we're going to start here. We're going to cross 0. And then we're going to cross at 3 halves. All right. So our graph is going to look like a parabola, even though it is a quartic. Remember, the maximum number of times it could cross the x-axis is 4. This particular one only crosses 2. So the quartic looks like a quadratic. And that would be kind of as accurate of a graph that I would want you to make. Once again, we do not know how high this goes. We don't know how many other squiggles it has in here. For help, I recommend putting this into your graphing calculator or a graphing app and kind of figuring out what goes on in here if you don't know how to sketch it. But more importantly, I'm looking at, do you know this, this, and this? Sketching it at the end is kind of not even at all the most important part, right? The individual pieces of this are much more beneficial to you as you go into higher level maths than this actual sketch. Okay, let's move on to another example. Okay, our next example is going to be f of x equals 2x to the third plus x squared minus 8x minus 4. First thing I'm going to determine is the ending behavior of this with the leading term test. So we look at the leading term. Our leading coefficient is 2. 2 is positive, and that means that the right side rises. Okay. Then we look at our degree. Our degree is 3. 3 is an odd number. So our left side does the opposite of what the right side does. The right side rises, so the left side falls. So that is needed information right there. Then we are going on to finding the zeros or the x-intercepts, the solutions, the roots, whatever you want to call it. We're going to find the zeros next. We're going to use the zero product property here. So 0 equals 2x to the third plus x squared minus 8x minus 4. First thing we try to do is we try to find the greatest common factor of everything. I see divisible by 2, divisible by 2, divisible by 2, but this x squared is not divisible by 2, so there is no GCF. So I see a 4-term polynomial that I'm going to have to factor by grouping. So the greatest common factor of the first 2 terms is x squared. That would leave me with 2x plus 1. And then the greatest common factor of the second 2 terms that leaves me with 2x minus 1 or 2x plus 1 is -4. And that would leave me with 2x plus 1. So 2x plus 1, we have the binomials being the same, so we factor those out. And then we're left with x squared minus 4. We have to make sure this is factored completely. 2x plus 1 is good, but x squared minus 4 can be factored further. That is a difference of 2 perfect squares. So x plus 2, x minus 2. So our zeros are -1/2, -2, and 2. All have a multiplicity of 1. So our zeros are -1/2, -2, and 2. Last thing that I want to find is I want to find the y-intercept. The y-intercept is the constant term. So we have a constant term of -4. So our y-intercept would be 0, -4. So let's look to sketch the graph of this. So we have 1, 2, 3, 4. So at -4, I'm crossing, and then I am at -2, I'm at -1/2, and then I am also at +2. So at -2, 1/2, and 2, I have my x-intercepts. And then I am going to rise to the right and fall to the left. Sometimes putting these arrows in ahead of time, before you actually draw the line, is a little tricky. But we're going to start down here. These are all multiplicities of 1, so I'm crossing once. So I have to cross -2, switch around, and cross -1/2. Cross through -4, then I have to switch back around and go through 2, and then end at my rises to the right. So my graph of that polynomial is going to look something like that. One more example to go. So example 3, we have g of x equals x to the 4th minus 7x to the 3rd plus 12x squared plus 4x minus 16. Now they're polite enough to give us the factored form of it, x plus 1 times x minus 2 squared times x minus 4. Because this is a 5-term polynomial, we do not have the skills yet in order to factor that. You will learn how to break this down in MAT176 pre-calc. Okay, so let's start by looking at the ending behavior of this graph. The ending behavior is based off of x to the 4th. We want to look at the original polynomial for that. All right, so their ending behavior, we look at the x to the 4th and realize that the leading coefficient of that is a 1. So 1 is a positive number. So that means that our right side rises. Then we look at the degree, and we have to look at the original polynomial for that. We have a degree of 4. 4 is an even number. So that means that our left side is going to do the same thing as the right side. So our right side rises, so our left side rises. That is our ending behavior. Next, we are going to look at our zeros. For our zeros, we have to look at our factored form. So we have g of x equals x plus 1 times x minus 2 times x minus 2 times x minus 4. So I wrote the x minus 2 twice. So 0 equals x plus 1, x minus 2 times x minus 2 times x minus 4. Then we're going to take each of these binomials and set those equal to 0. This is the zero product property. So x equals -1, x equals 2, x equals 2, and x equals 4. So that means that we have zeros of -1, 2, but 2 has a multiplicity of 2 and 4. So -1 and 4 have multiplicities of 1, but 2 has a multiplicity of 2. Last thing that we have to talk about is we have to find our y-intercept. Our y-intercept is our constant term. So our y-intercept is 0, -16. So we have our ending behavior, we have our zeros, and we have our y-intercept. That is enough for me. So something's going to happen at -1, then again at 2, then at 4. Then also something's going to happen at 0, -16. All right, -16. I don't feel like making all those lines, so I'm just going to put it somewhere down there. Now our ending behavior, we have our right side rising and our left side rising. We have a multiplicity of 1 at -1, so we're going to cross through -1. We're going to cross through -16. We're going to bounce off 2 because there's a multiplicity of 2. Come back around and go through 4 because there's a multiplicity of 1 there. So I'm going to start at my left side rising. I'm going to cross through -1, come all the way down here through -16. Spin around. I'm going to bounce off 2, come around, spin around, head back up towards 4, and then go to my right side rising. My graph could look something like this. Once again, I do not know how low this goes past that -16. I don't know how high or low this goes. It might look like a different shape. But it's going to cross through -1, cross through -16, the y-intercept, bounce off 2, cross through 4, and the left and the right side are both going to rise. That is section 4.2. Once again, these 3 steps are more important than that sketch. So if the sketch is actually giving you some problems, I'm more interested, do you know how to find any behavior, the zeros, what the multiplicities mean, and how to find the y-intercept. This right here, wrapping this all together, that is the last thing you should worry about, okay? I will talk to you soon. Thank you.